Welcome to the Purdue Global Academic Success Center's presentation on carbohydrates. In this seminar, we will cover the following learning outcomes: describe functional groups, their importance in organic compounds, monomers and polymers, briefly state what carbohydrates are, describe classification of carbohydrates and give examples, and describe anabolic and catabolic reactions. Functional groups are groups of atoms within a molecule that have a consistent, specific behavior and distinctive chemical properties called functional groups. The atoms in a functional group are linked to each other and to the rest of the molecule by covalent bonds. Examples of functional groups include the hydroxyl group, ketone group, amine group, and ether group. Functional groups are important in chemistry because they are the portion of a molecule that is capable of characteristic reactions. They, therefore, determine the properties and chemistry of many organic compounds. Monomers. When a few functional groups join a carbon chain, they create a simple molecule called a monomer. Monomers are small molecules, mostly organic, that can join with other similar molecules to form very large molecules, or polymers. All monomers have the capacity to form chemical bonds to at least two other monomer molecules. Some examples are glucose, vinyl chloride, amino acids, and ethylene. Polymers. Monomers combine to form complex molecules called polymers. Every monomer can link up to form a variety of polymers in different ways. For example, in glucose, glycosidic bonds that bind sugar monomers to form polymers such as glycogen, starch, and cellulose. Macromolecules are long, repetitive sequences of an elementary chemical structure called the monomer. A macromolecule is a very large molecule composed of thousands of covalently bonded atoms that plays an important role to biophysical processes. For example, monosaccharides, which are monomers, join together to make carbohydrates, which are polymers. Living organisms are made up of four macromolecules: proteins, carbohydrates, lipids, and nucleic acids. In chemistry, carbohydrates are a common class of simple, most abundant, and widespread organic compounds. A carbohydrate is an aldehyde or a ketone that has additional hydroxyl groups. Carbohydrates serve as metabolic energy sources. Carbohydrates are the nutrients most frequently used as an energy source, containing 4 kcal per gram, as they are fast-acting and turn into energy as soon as they are ingested. This energy powers the brain and the body. The energy that powers the body and brain is generated when carbohydrates are broken down. They have C, H, and usually O atoms. The simplest carbohydrates are called monosaccharides, which have the basic structure CnH2O, where N is 3 or greater. Carbohydrates are covalently bonded. Carbohydrates are made up of monosaccharides linked together into polysaccharide chains by a type of covalent bond known as glycosidic bond. Carbohydrates are called saccharides, which is Greek for sweet. Carbohydrates are considered essential constituents of all living things. Why? Because carbohydrates, fiber, starches, and sugars are essential food nutrients that your body turns into glucose to give you the energy to function. Complex carbs in fruits, vegetables, and whole grain products are less likely to spike blood sugar than simple carbs, sugars. Extra info. Why is carbohydrate the most abundant? Carbohydrates are the most abundant class of organic compounds found in living organisms. They originate as products of photosynthesis, an endothermic reductive condensation of carbon dioxide requiring light energy in the pigment chlorophyll. The carbohydrate stoichiometric formula is CH2ON, in which N is the number of carbons. Carbohydrates contain carbon, hydrogen, and oxygen in a 1 to 2 to 1 ratio. The common component, carbon, C, carbo, and the component water, H2O, hydrate, give the name to this group of organic molecules. Some carbohydrates are isomers, molecules with the same molecular formula but different structures. Some examples are glucose, galactose, and fructose. The classifications of carbohydrates includes simple carbohydrates and complex carbohydrates. Simple carbohydrates, monosaccharides, disaccharides, and oligosaccharides are the basic type of carbs. Soft drinks, candy, cookies, and other sweet snacks contain simple carbohydrates. Complex carbohydrates, homopolysaccharides and heteropolysaccharides, represent an important energy source for your body. They provide the sustained fuel your body needs for exercise, daily living activities, and even rest. Simple carbohydrates include monosaccharides, disaccharides, and oligosaccharides. Simple carbohydrates have 1 or 2 sugar molecules. They are digested and converted quickly in the body. Before they can be ingested into the gastrointestinal tract, food carbohydrates have to be broken down into monosaccharides. They also flow in the monosaccharide form in the blood. They are abundantly found in milk products, beer, fruits, refined sugars, and candies. Honey is a natural sugar as well, and people eat natural sugar in its original form. Simple carbohydrates are easier to handle because they are less, or simpler, complex. Complex carbohydrates include oligosaccharides and polysaccharides, homopolysaccharides, and heteropolysaccharides. They contain 2 or more sugar molecules. Complex carbohydrates are made up of sugar molecules that are strung together in long, complex chains. They are digested and converted slowly in the body. Complex carbohydrates have fairly long-lasting energy. They can be found in lentils, beans, peanuts, potatoes, peas, corn, whole grain bread, and cereals. The majority of carbohydrates should come from complex carbohydrates, starches, and naturally occurring sugars, rather than processed or refined sugars, which do not have the vitamins, minerals, and fiber found in complex carbohydrates. Monosaccharides are the simplest carbohydrates. They conform to the general chemical formula CH2OX and are termed simple sugars. Monosaccharides, also called simple sugars, are made up of 3 to 7 carbons, and they can exist as linear chains or as ring-shaped molecules. Monosaccharides are signified by the suffix OSE, ose. Some examples are glucose, fructose, and galactose. Disaccharides are also called double sugars. A disaccharide is a substance that is composed of 2 molecules of simple sugars, monosaccharides, linked to each other. They are crystalline, water-soluble compounds. Disaccharides are those carbohydrates that will undergo hydrolysis with acids or enzymes to give 2 molecules of monosaccharides, which can either be the same or different. The 3 major disaccharides are sucrose, lactose, and maltose. Oligosaccharides represent carbohydrates that contain between 3 and 10 single sugar residues. They're not relatively abundant in the diet when compared to other, more common carbohydrates like those in the disaccharide category. Common oligosaccharides include raffinose, stachyose, and verbiscose. A large number of oligosaccharides have been prepared by partially breaking down more complex carbohydrates, polysaccharides. Most of the few naturally occurring oligosaccharides are found in plants. Raffinose, a trisaccharide found in many plants, consists of mellibiose, galactose and glucose, and fructose. Other examples are stachyose and verbiscose, which can be found in relatively abundant levels in legumes, whole grains, vegetables, and some fruits. Complex carbohydrates are composed of 10 to up to several thousand monosaccharides arranged in chains. Special enzymes bind these small monomers together, creating large sugar polymers or polysaccharides. A polysaccharide is also called a glycan. Polysaccharides are the most abundant carbohydrates found in food. Starch, glycogen, cellulose, and chitin are primary examples of polysaccharides. Their functions include the storage of energy. Many polysaccharides are used to store energy in organisms. As the side chains of the monosaccharides form as many hydrogen bonds as possible with themselves, water cannot intrude on the molecules, making them hydrophobic. This property allows the molecules to stay together and not dissolve into cytosol. Cellular communication. Glycolipids and glycoproteins can be used to send signals between and within cells. Cellular support. By far, one of the largest roles of polysaccharides is that of support. All plants on Earth are supported, in part, by the polysaccharide cellulose for structural support. Other organisms, like insects and fungi, use chitin to support the extracellular matrix around their cells. Everything from the wood in trees to the shells of sea creatures is produced by some form of polysaccharide. Polysaccharides are divided into two categories: homopolysaccharides and heteropolysaccharides. A polysaccharide can be a homopolysaccharide, in which all the monosaccharides are the same, or a heteropolysaccharide in which the monosaccharides vary. A homopolysaccharide is classified as a chain that contains only one type of monosaccharide unit. Some examples are glycogen, cellulose, insulin, and starch. Whereas a heteropolysaccharide contains two or more types of monosaccharide units. Some examples are a heparin and hyaluronic acid. Glycogen is composed of long polymer chains of glucose units, which are bonded with an alpha-acetyl linkage. This acetyl linkage forms by the combination of the carbonyl group and the alcoholic group. Glycogen is a homopolysaccharide found in the liver and muscles of animals, where it is used to store energy. Chemically, glycogen is related to starch and closely resembles amylopectin. Some of the important heteropolysaccharides include hyaluronic acid and heparin. Hyaluronic acid is made up of D-glucuronic acid and N-acetylglucosamine. It's found in connective tissues and skin. Heparin is made up of D-glucuronic acid, L-iduronic acid, and N-sulfo-D-glucosamine and is largely distributed in mast cells and blood. Anabolic reactions involve the building of larger, complex molecules from smaller, simpler ones, and they require an input of energy. The dehydration synthesis reaction is the creation of larger molecules from smaller monomers where a water molecule is released. Why are dehydration synthesis reactions considered to be anabolic? Anabolic reactions involve the joining of smaller molecules together to form larger, more complex molecules. This occurs through dehydration synthesis reactions. Catabolism is the breaking apart of molecules to smaller molecules to release energy. An example of a catabolic reaction is digestion and cellular respiration, where you break apart sugars and fats for energy. Hydrolysis is the way in which this is done, and it is basically the reverse of a dehydration reaction. Hydrolysis, hydro equals water, and lysis equals break, involves adding water to one large molecule to break it into multiple smaller molecules. Why are hydrolysis reactions considered to be catabolic? Hydrolysis reactions break covalent bonds by consuming a water molecule and dividing its atoms between separate molecules. These reactions are catabolic. In other words, catabolism is the process of breaking down complex molecules into simpler molecules. Thank you.